So welcome to our seminar series in the Gemini Center on Quantum Computing. Our speaker today is Jeroen Danon. Jeroen has a PhD from 2009 from the Delft University of Technology, where he studied hyperfine physics in semiconductor quantum dots. From 2009 to 2012, he was a postdoc at the Free University of Berlin, where he continued his work on quantum dot physics, but he also worked on different things, including persistent currents, quantum transport and quantum transport in ferromagnets. From 2012 to 2016, he was a postdoc at the Niels Bohr Institute in Copenhagen, where he studied Majorana-bound states in semiconductor nanowires and the physics of superconductor and semiconductor hybrid systems. From 2016 on, he is a tenure-track associate professor at NTNU, where he continued his work on aforementioned directions. And he also got a Young Research Talents grant from the NFR in 2018 on the topic of quantum dot-based spin qubits. And so most of his work emphasizes on this in the past few years. Today, Jeroen will give a presentation on solid-state spin qubits, where he will present a personal view on the development of the solid-state quantum dot-based spin qubits over the past 2 decades. So I think it's fine if you go ahead and take it from here.
Yeah, sure. And indeed, maybe just if you feel the need, just interrupt me. I mean, it's maybe good if you have a question to address it. Yeah, so actually my plan is a little bit, so the general plan of this talk is I want to basically give a non-physicist, most of you are non-physicists, an idea what a theoretical physicist like me means when we say, yeah, you know, I work on qubits. So what do we do? What's the type of things we think about? And for that, I indeed picked the topic of spin qubits. First of all, indeed, because it's one of my own main expertises. So I work a lot in this direction. And secondly, because I think it's actually a very simple thing to explain. So, you know, also the non-physicists should get an idea. This might, if there are, I know there are a few physicists in our center as well, and maybe this will be a little bit on the easy side for you, this talk, but so be it. Yeah, so spin qubits, they are actually as simple as it sounds. If you did one course in quantum mechanics or so, then you know that every electron has a property called spin, can be up or down. It's a 2-level system, and in that sense, it's a qubit, right? So in principle, every electron around us is a free qubit, and we could use it for a quantum computer. Well, that sounds great, but of course, everyone would immediately say, well, you know, yes, there are plenty of electrons around, but catching one of them and, you know, doing something to the spin and then read it out or manipulate it, that sounds pretty hard. So maybe this is not such a simple idea. And the answer is yes, it is pretty hard, but actually we can do that. So nowadays in labs, people are able to catch, as I said, catch a single electron and do something with its spin. And for the people who don't know about this, I will use now a few slides to just sketch very roughly how this is, or one of the ways how this can be done, sort of the classical way how this has been done in the past few decades. And it's all based on a technique which I think was developed in the 60s, 70s. So after we started understanding what a semiconductor is from quantum mechanical point of view, you know, the band structure and everything, people started being smart and say, wait, but if we take different semiconductors with different properties and we stack them on top of each other, we can actually engineer this band structure a little bit, you know, as a function of when you go through this sandwich. And even if you don't know any solid state physics and band structure doesn't really ring a bell, then still you might believe me if I say, well, you take different materials, they're all in between conducting and insulating. And if you do it in a smart way, you could end up with, say, a very thin plane where electrons actually can move around, that conducts, and an insulating, the rest of it is sort of insulating. And if you have that, it sounds like, okay, sure, then things are a little bit smaller, so what? No, because what you have is actually a real two-dimensional world for the electrons, and in many ways that is very fundamentally different from like the three-dimensional world we live in. One example they discovered after making these two-dimensional electron gases, they discovered if you apply a out-of-plane magnetic field to such a two-dimensional world, you can end up with a very special state of matter. It's called the quantum Hall effect. It's in fact a sort of a topological state with edge modes, and it's so different from what we can do in 3D that it took some while to understand what was going on. It actually brought 2 different Nobel Prizes, and it's super interesting physics. So that has been going on for many decades, actually, playing with these 2D worlds. But then based on that, people realized after a while, wait, what if we take our two-dimensional, this whole sandwich with the two-dimensional world here, and what if we make sure that there's some, insulation on top, and then we put some metallic gates there, and let's say we put a negative voltage on these gates. So then there will be an electric field locally here and here. And one of the things it will do is will push away electrons below it, right? I mean, also negatively charged, so they like to, repel each other, negative charges. And then you can imagine, for instance, if you make a structure like this, you look from the top, it looks like this. Say under these 2 gates in the two-dimensional world, the electrons are pushed away. So it could look like this. And what do you effectively have then? Well, actually, you went from a 2D world to, say, an almost purely 1D channel. Sounds still a little bit boring. I mean, a wire is also a wire. What's so special about it? But if you do this and you make it small enough, you can actually see that you can make perfectly conducting one-dimensional channels, where as a function of the channel width, you measure not like a nice, a smooth curve that goes up. If you would measure conductance, so how easy is it to squeeze electrons through this channel? Sure, if it's wider, you get more electrons through, but you see a stepwise function. And these steps are really related to the transverse, say, particle in a box, quantum mechanical states of the electrons traveling through this channel. So narrow is it. So here, this first plateau, you have a truly one-dimensional world. And that's, again, completely fundamentally different from 2 or 3D. When that was done, then, of course, the last step, you feel where it's going. Of course, you can go even further and say, let's call it a quasi-zero dimensional system, basically a particle in a box. You can make a small island, and that's routine nowadays. It's no problem to do. So you have one island here where the electrons can live. I listed some of the typical properties of these islands, numbers. It's not super important. The message here is that these islands, it's no problem to make them small enough that you can actually be sure, if you go at low enough temperatures, that you have trapped one single electron, or 0, or 2. You can actually see it happening, and you can control it one by one. When this was discovered in the 90s, first people were just excited about the basic physics, like, wait, this is actually in a way an artificial atom where we can load electrons one by one in particle in a box states, and just like shells around around the nucleus. And that was all, several very nice works. But very soon after this was sort of, clear that this was an option, of course, now the proposal how to actually, create a spin qubit using this technique was put forward. And it's very obvious in a way, this proposal, and straightforward, but it lists the things you need. So let's just quickly see how this was, how this was put forward. Of course, we now have our islands. Suppose you have one electron in each of these islands. It has a spin. That's a qubit. How do you operate your qubit? Well, just straightforwardly thinking, manipulating a qubit, what do you need? You probably need some magnetic control. Spin talks to magnetic field, so preferably an oscillating magnetic field locally on the site of the particle in the box, and that's a way you can manipulate spin. If you want to have 2 qubit gates, that's in a way a bit easier. You just, you allow for quantum mechanical tunneling between neighboring dots. Then these spins talk to each other through exchange interaction or the Pauli principle. Depends how it's all related. But in fact, opposite spins and parallel spins will just interact slightly differently, and that just provides you with a 2 qubit gate, if you will. And then finally, let's not go through the details, but of course you need to initialize and read out, and there are smart ways. You basically you can use this Pauli principle as well, or something else that in the end translates the spin state into a signal you can measure, like a current or a charge hopping from left to right. That's not an issue. There are good ideas how to do that. And this was sold in a very nice way, saying that, well, our qubits are now spins inside these semiconductors, and if there's anything bad going on inside the semiconductors, it's only charges. It's there are donor sites, there are crystal impurities, random charges hopping around. There will be a lot of voltage fluctuations, but there will be no magnetic field fluctuations in principle. So that makes your qubit very, very stable in theory. And the second selling point was, well, it's actually a pretty scalable design. If you look at this top picture here, you can imagine making 1 island, you can imagine making 1,000,000 islands without any, qualitative barrier to overcome. And especially if you think about what you need, a bunch of semiconductors and a bunch of conducting materials etched on top. That's exactly what the whole semiconductor industry is doing every day. And in principle, if we figured out how the optimal system is going to work, in principle we can just send the design to Intel, and tomorrow they can make a whole quantum chip with 1,000,000 qubits on it. So in principle, I'm not saying that this is what happened or is going to happen this year or so, but in principle that was the idea. Like, okay, this is scalable, it's compatible with current semiconductor technology, and it's a very stable qubit. Okay, so that sounds great. So why are we now 20 years further down the road and don't we have a spin qubit quantum computer? Oversimplifying the issues, I think there were 2 big problems with this idea. One is a fundamental thing. No one thought about it in the beginning, but it was figured out pretty quickly. This material, our favorite material, gallium arsenide, turns out that both gallium and arsenic, the atoms have a finite nuclear spin. And that spin talks to the electron spin you're catching inside the semiconductor. If you want, this is the Hamiltonian. It's an interaction. It can be seen in a simple picture as a sort of a random, so all these spins together act as a random magnetic field talking to the electron, adding to the field you're applying. And that's bad news because it's random and it's not super large. It's about 5 millitesla, turns out to be in a typical system. But if you translate that to a decoherence time, there's, something is rotating your phase and you don't know how fast it's going. That's decoherence. That's typically tens of nanoseconds. And that's too short. That's just not going to work if that is how it is. So that's one big problem, was one big problem. And the other one is slightly more, it's easy to say, well, if you want to operate your qubit, just apply a local oscillating magnetic field. But in practice, it's almost impossible to create a magnetic field that's localized on a 20 nanometer scale, and it's not talking to any of the other qubits that are nearby. That's just from practical point of view, not going to work in principle. So I would say that roughly in this field, much of the work in the past 20 years was aimed at solving these two issues. And let me just, flesh a few of the approaches we tried to use in the field, and also then highlight why it actually leads to interesting physics and not just, not just engineering in a way. For instance, this Hyperfind problem, what could you do? One thing, and that's the most, I would say, the most interesting, but maybe also most complicated solution is, you could say, well, it's not just a random field acting on the electron spins, the problem, it's an interaction. My electron also talks to the nuclear spins, you know, these arrows here go two ways. So in principle, you could imagine doing some, you have control over the electron, right? So you could do something to your electron, and if you repeat that, and you do pick something smart, you set its spin in a certain direction, and then again and again and again, that will actually start affecting the polarization of the nuclei. And in principle, you could end up in some sort of feedback cycle where you do something to your electron, your nuclear spins change, that affects how the electron, the total field acting on the electron, etc., a cycle. And we found several cycles you could run that actually result in a suppression of the randomness of the nuclear field. That's very nice, but in the end, as I already said, they were all quite involved. You need to do something quite complicated. And then you could say, well, if you do that for 20 seconds, then you know that for a short while, your nuclear spins are not really random anymore. Could work, but it's not ideal, right? But in a way, why am I highlighting this? It is actually a very interesting physics problem, right? I mean, just basic quantum mechanics. You have one, we call it central spin problem. You have one spin that's talking to a whole bunch of spins, quantum mechanically. That is, you know, a non-trivial sort of textbook quantum mechanics problem. And now we have systems in labs where they're playing with this, and then you can think about it, and you can, you know, try to understand what they measure, and then give new ideas. Why don't you do this, and see if indeed the simple model works, etc., etc. So this, I think, is also from a fundamental physics point of view very, very interesting. Not only to, you know, get better coherence times, but just to study the central spin model. Other approaches, just flash, do something smart with, you know, basically filter out the effect of the nuclear spins, apply a lot of pi pulses to all your qubits all the time with you know, very special spacing in time. Might work, did work very nicely in one experiment, still very complicated. You don't want to run your quantum computer in that way. Simplest, most boring, but again, in the end, also interesting solution. Gallium, gallium arsenide, the two atoms both have nuclear spin. I said 3/2, in fact. But as you know, every atom, every isotope of an atom has a different nuclear spin. Turns out that silicon and germanium have a very common isotope with 0 nuclear spin, right? Problem solved. Turns out that silicon has disadvantages from the particular type of how the band structure looks. It was harder to grow it in a nice way, but they're catching up. And actually, this problem with the band structure, I'm not going to go into it, leads to interesting physics. It basically gives you extra degrees of freedom when you want to, you know, you catch a single electron, there's not only spin, there are extra degrees of freedom due to the band structure. That's also very fundamental, very interesting physics to think about and to play with. And again, you can just, you know, many labs in the world are doing this, so you have, you know, a real connection with reality. Okay, so that's about the Hyperfind problem. What about the other problem? Also there are more boring and more interesting solutions, more creative, more straightforward. One approach that has been developed in the last 15 years is why not use more spins to encode a qubit? What if you take 2 spins in 2 neighboring dots, then of course you have 4 allowed spin states, and you pick 2. Suppose you pick the triplet and the singlet, which both have total angular momentum 0 projection along the direction of the field. Then you have 2 states that basically talk in the same way to a magnetic field, but they talk differently to each other. If we bring them closer together, then one of them basically has parallel spin, the other one has anti-parallel spin. So exchange effects will be different for these 2 states. So if this is your qubit, then say in the qubit subspace on your Bloch sphere, just by playing with the coupling, the tunnel barrier between the 2 dots, you have control over one of your qubits. You're basically the qubit splitting, say the field along the z-axis of your Bloch sphere. You can control it by playing with the tunnel barrier. So you don't need a magnetic field. You don't need an oscillating magnetic field. Turns out, okay, one control axis is just one. Turns out, if you're smart and you go one step further and you put 3 electrons in 3 neighboring dots, then you have 2 tunnel barriers you can control. That actually, in this way, you can pick 2 out of the 8 states you have now and define a qubit in it, and you can control that qubit completely electrically by playing with these couplings. That's very nice. Of course, you pay a price. The more you use this exchange interaction and tunnel couplings as handles in your qubit, the more sensitive the thing becomes to charge noise per definition, right? But it works, and I think it's just nice to show because, you know, it's sort of creative, out of the box thinking, and that's also stuff we do in my field. Slightly less, how do you say, slightly more boring solutions for this control problem is, say, use a material that has strong spin-orbit interaction. If you don't know what it is, it just tells you that if you move an electron around, something starts talking to its spin. It's a relativistic effect, and it can be strong in semiconductors. And if you have one with strong spin orbit, sure, and you shake your electron just using electric potentials, and effectively it will see an oscillating magnetic field. Works. Although the downside is that this spin orbit will also start messing up your spin when you don't want to, you know, when you don't want to operate your qubit. So there are upsides and downsides. Even more sort of stupid or engineering thinking is, well, just place on your sample a tiny magnet that has, you know, not a uniform field, but so tiny that the magnetic field is pointing in all directions. Then, of course, if I take my electron and I shake it a little bit around, there's a position dependence in the field, and shaking the electron in space will make it feel an oscillating magnetic field. And sure, it works, and actually some groups are now using this as a standard way for, you know, for operating the qubits. So that's nice. And I'm almost getting towards the end of my talk. Let me just, to be even more specific, if you would ask, okay, sure, but what are the things you are interested in? What do you do? I can give you 2 examples of the last, what is it, 2 years, I think, 2 or 3 years of things I did with my students. And they both fall in, you know, in these categories we just discussed. First of all, I was thinking about these triple dot qubits because they have such nice control. You don't need magnetic fields, but they still have this hyperfine nuclear spin problem. So we thought a lot about it, and then we actually found a way. It's a little bit, you know, it's also not ideal if you would have to do this all the time, but it's nice, you know, it's a creative solution. Turns out that if you run a current through the system, you put one electron here, one here, and you run a current in a sort of a T-shaped setup. So electrons enter here, and they can go to the left to a drain reservoir or to the right to a drain reservoir. Turns out that this actually leads to one of those feedback cycles that automatically starts suppressing the bad parts of the nuclear field fluctuations. No time to go into details, of course, so you just have to believe me, but it's this magic of, you know, the fact that it's an interaction and that you do something to your electrons that starts talking to the nuclei, that starts interfering with how the electron wants to behave. And turns out that if you do it like this, that the system automatically starts suppressing these fluctuations. Actually, no one tried this so far because the field moved a little bit, you know, emphasis is constantly shifting. And of course, you need to make a completely new system with an extra injector here and 2 drains on 2 sides. So, but you know, you never know. They could, people could give this a shot at some point. Another sort of very creative, but in a way very straightforward idea we put forward is, well, we went from 1 to 2 to 3 spins to solve problems, and there's 1 problem left. What should you do? Of course, you go to 4 spins to solve the problem. That sounds like a joke. It was almost a joke when I started thinking about it, but actually, and that is maybe some of you guys who are into more, you know, error correction, quantum information theory, you might know, if you go to 4 qubits, 4 spins, you end up in theory with a so-called decoherence-free subspace, where you have two singlets that in principle are immune to global, what's called global decoherence. And that's not what we have. All these hyperfind fields are local, but it also suppresses, it makes the effect of local fluctuations higher order. Physics way of saying this is, well, if I have 4 spins, I have 2 different singlets. Singlets have spin 0, total spin 0. So both my qubit states have spin 0. So if there's a field, no matter what kind of field, as long as it's a, you know, a Zeeman-like interaction, is just a field coupling or a nuclear field coupling to spins, it won't couple to a singlet. The singlet is spinless, so it doesn't care about fields. And we worked it out. Of course, that was sort of known, but what we did was thinking about, okay, indeed, we have to use 4, but how do you squeeze them into a solid state quantum dot system in a way that you can actually do something useful? And it turned out very nicely that the most straightforward way is put the 4 dots with 4 electrons in a T shape. And then actually, that's what we figured out. You can operate this thing exactly like this triple dot thing. So if you pretend this row of 3 in the bottom is your triple dot, you play with the tunnel barriers as before, you get exactly the same qubit control. Again, this has not been tried so far because it's easy to say, oh, just make 4 in a T shape, but that's not something people have lying around in labs. So then we moved on. We thought, well, it would be great if we could squeeze it in fewer dots. I mean, the key ingredient is 4 electrons, not 4 dots, right? Turned out, for reasons I'm not going to go very much into right now, if you use 6 electrons, then 2 of the 4 on a central dot are the 2 you're basically using. The other 2 are sort of inert, but you need 6. Then you can actually squeeze it in a triple dot setup. And this we realized 2 years later, and then we published this as well. And actually, for this one, I have been contacted by 2 experimental groups that were so excited about this idea that they're actually right now they're trying to do this, to make the singlet only thing and show that it's much less sensitive to these nuclear spins. So that's just 2 examples, and that basically brings me to the end of my short presentation. To summarize, you know, it sounds like this field is now 25 years old and didn't get anywhere really yet. If you look at, you know, the actual results compared to these Google quantum computers that all use superconducting qubits, but still, you know, it was proposed end of the 90s, and then a few years later, first qubit oscillations were seen. And I would say, you know, this is how exactly the same experiment looks nowadays. So there is definitely a lot of progress. I think people are now, we have published papers about a 4 qubit quantum processor, I think 6, and I think they're now working on the two-digit number of spin qubits. And, you know, progress is steady, and that makes us very hopeful. So maybe in a few years, we will actually also have not only superconducting, but also spin-based quantum computers with potentially, you know, this whole potential to use standard semiconductor fabrication to scale up and make this work. Because, you know, superconducting qubits are nice, but first of all, you need superconductors, but, you know, there are also ways around, you know, you could use maybe nice high TC superconductors at some point, but they're also relatively big, these qubits. You need some RC oscillators, and, you know, they're much bigger than these quantum dots we are using. So if you were thinking millions of qubits, then actually this spin qubit might be more promising in the long run. Okay, so, you know, where are we now? I would say, looking back on this whole story, actually silicon and germanium, which are nuclear spin-free, are now catching up, and most groups are moving towards using that. You can even be smart if you don't like the band structure for your electrons to use what we call whole spins, or remove electrons from the valence band. It's very attractive, leads to interesting physics, because valence bands are typically more complicated in a different way than conduction bands. You can stop listening if this is too technical, but I just want to highlight a few points. We actually have qubit coupling not only working in the original proposal like neighboring spins, but we can use microwave resonators, superconducting resonators to couple qubits that are actually centimeters apart. So, you know, things are coming together. You could ask, okay, for you as a theoretical physicist, is there anything interesting left? As I said, just to mention a few things, as I said, these Hall spins, people are using Hall spins. The dynamics are much more interesting than for electrons. You get a very complicated spin and orbital dynamics, very interesting, nice that you can play with it in the lab. Qubit coupling over slightly shorter length scales would be nice. Now we have the options neighbors, that's 10 nanometers, or microwave resonators, that's a centimeter. Ideally, for an actual quantum chip, you would, you would like to have something in between. Then every qubit you can control with electric fields is sensitive to charge noise. So we have to understand that step by step better to fight it. Let's see, what did I write? Yeah, the bigger your systems become, the harder it becomes to tune them in the lab. Tuning one quantum dot to have only one electron in it is already hard. Imagine having 1,000,000 quantum dots and they all crosstalk. Loading an electron to number 12 changes the electric field on number 11 because of the extra electron. So maybe there at some point we have to switch to smart tuning strategies using machine learning, things like that. And, you know, always try to be creative, maybe look into more decoherence-free subspaces like the singletonic qubit. What can we do? How can we be creative? So, you know, I think there's still plenty of stuff to do, and it's not just engineering of scaling up. There's still a lot of interesting physics there. Yeah, so that was what I prepared. That is 29 minutes and 59 seconds. I guess that was sort of as planned. And yeah, so if there are questions, maybe I should keep the slides open. Now is the time then.
Yeah, thank you very much. Are there any questions from the audience? Please go ahead. Maybe I can start with one of my own, which might be
Sure.
a bit ignorant, but you showed some pictures, I think it was slide 12. Yes, these lines, the picture from Quist and Danon PRB20.
Oh yeah.
Are these, it seems like you always say you're not doing this in reality, but this seems to me like a really noisy real life plot.
Well, yeah, okay, good question. So well, that's, you know, partly the way I like to do research. I mean, we had this idea. I mean, this is a very complicated system, right? You have one electron spin and 1,000,000 nuclear spins. You're never going to solve it with pen and paper. So you make a lot of simplifications, and then you say, well, with my simple model, it looks like this is going to lead to a suppression of the fluctuations. And, you know, then I like to say, okay, but, you know, it is not so hard to do a numerical simulation where you take the actual interaction much more seriously and then just show that it indeed happens. That, you know, I think if I remember correctly, these dashed lines here are what our back of the envelope simplifications predict for the suppression of the harmful fields. And then the solid lines are just one run of a simulation with fluctuations, of course. Yeah, you take everything, you add some random, you know, simple model, but you add some random spin flips because, you know, there's always finite temperature and so. So yeah, that's why it looks like that.
Okay, thank you. Any more questions?
Can I ask?
Sure, just go ahead.
Yeah, just go ahead. Right. So this just on this same slide, this second example, you say it's being creative. So you're saying that it's quite a big step going to 4 spins and 16-dimensional Hilbert spaces. So the big step is it's about seeing that this can be done, or just so why would, I mean, how would you explain the creativity and the step of, you know, going to this type of dimension or this type of configuration?
There are 2 answers. For me personally, the creativity was to realize, oh wait, there are 2 singlets, but then you look into the literature and then it turns out that that is common knowledge among many people, especially, you know, as I said, quantum information theorists. But then actually for the field, the creativity was to say, okay, sure, 4 spins have 2 singlets, great qubit, but how do you translate that into an actual solid state system where you can say, look, and if you now put a voltage on that gate, you push that potential a little bit up, then you get a sigma x rotation. If you push on that gate, then you get a sigma z rotation. So translating it into a proposal like, look, this is how you put 4 electrons next to each other, and then these, you say, knobs in your experiment give you this control over your qubit. That is being creative is maybe if I would argue with a painter or composer, it's, you know, on a very small scale. But I mean, it's literally how we started. The idea was 4 electrons. First I thought, okay, let's squeeze them all into 1 dot, and then you do some calculations. Okay, no, that's not, you don't have enough control. Then obvious first thing, of course, was I looked at what's the physics of 4 dots on a row with 4 electrons. Turns out that that was slightly too symmetric in a way. I mean, it's a long story to explain. And then, you know, it took a few steps to end up with this T geometry, which is, from an experimentalist point of view, not ideal, but it's the simplest we could come up with that, you know, would give this singlet only subspace, but also very nice qubit control. So that was basically the journey we had for a few months.
Right, but can I also ask, is this the only way, or is it just one of many other ways? Do you know?
Ooh,
I mean,
the only
is the answer unique? I mean, just from as a mathematician, I would ask, you know, are there other ways to get there or to put this in this?
Depends a little bit on what you mean with there. As I said, if the goal is to code your qubit into 2 singlets, then, you know, having 4 qubits is the answer, period. And you're not even talking about how to arrange them geometrically. If your question is, I want to use these 2 singlet states, but I also want exactly the same nice control we had over these triple dot structures, then I think the 2 figures here are sort of obviously the 2 options. On a row, it's not gonna work in that way, maybe in a different way. So yeah, I don't know, is that sort of, it depends a little bit on what you want to achieve.
Yeah, no, I think I received an answer to my question was also a little bit just, yeah, not too precise, but I think I understand.
Okay.
Thank you.
Good.
Okay, perfect. I guess thank you one more time, and see you next time.
Yeah,